seminar. Today's speaker is Dr. Wang. Wanqiu got his bachelor's in China at the Nanjing Institute of Meteorology. And then he went to IAP, the Chinese Academy of Science, and got a master's degree there before coming to the US at the University of Illinois to get his PhD. After getting his PhD, he moved to NSAP and has stayed there ever since. And he's now a scientist at CPC, working on climate modeling and prediction. So we're very pleased to have him here. Today's talk is exploring the SST impact on tropical intraseasonal oscillation. So let's welcome him.
Yeah, thanks for the introduction, and thanks for inviting me. Good afternoon. Tropical intraseasonal oscillation was the topic I worked on for my PhD dissertation. That was 20 years ago. So at that time, I thought the problem would be soon solved. Now 20 years passed. Many people, more and more people joined the MJO study club, and numerous papers published on MJO or aspects of MJO. But the prediction simulation problems are still there. And now I think it's very it's likely that the problem will not be solved soon. And this means that MJO is a complicated system, and it's very difficult to understand and improve the simulation and the prediction. So either something fundamental is missing in the model that we just don't see it, or because the MJO is affected by many factors, so our understanding or improvement need to be step by step, a little by little. So today I'm going to talk about a small aspect in MJO simulation prediction. That is the impact of SST. I think everybody knows MJO. So MJO is one of the two major modes in the tropics. But I just want to use this figure just for a brief discussion and just the introduction for the completeness of the talk. So here we are looking at the MJO, composite MJO, as a function of the longitude and phase. So we see the enhanced convection in phase 3, which is shaded. That is OIR, and to the east we see easterly anomalies. That is 200 millibar wind. So in phase 3, it's enhanced in the tropic and in the ocean, and in phase 6, the convection moved to Western Pacific with consistent zonal winds. So that's the one of the modes in MJO. So another mode is boreal summer intraseasonal oscillation. That is observed in summer, which is also called monsoon intraseasonal oscillation, MISO. And here we look at a similar thing. So this oscillation is characterized by enhanced convection, which is OIR here, propagate northward and eastward. So in phase 4, it has a northwest and southeast band from India to Western Pacific. This is followed by suppressed convection and propagate northward and eastward again, and having a northwest east southeast band from India to West Pacific. So what's the importance of the intraseasonal oscillation, and how well do model simulate and predict them? Studies have shown that MJO affects weather and climate over the globe at different time scales, including tropical cyclones, extratropical cyclone activity, India, Australia, summer monsoon, American climate, Arctic oscillation, and so many things. Similarly, MISO also modulates regional weather and climate, and this oscillations are the predictability sources for weather and climate system. But there are still systematic errors in the simulation. So all models, most models, tend to produce standing oscillations and are unable to simulate the propagation across the maritime continent. For the prediction, the model tends to predict more slowly propagating oscillation with weaker amplitude. So just to give you an idea how the model simulations are, here is a CMIP 5 simulation calculated as a rainfall lag correlation between anomalies at each longitude with itself at a point in the Indian Ocean. So the upper left two panels are observations, which shows a very nice propagation. And the other 20 panels are from models, many models. Out of those 20 models, only one model shows relatively good simulation, although still slower probably than observation. All other models are either really slow or just locally oscillating. So that is simulation. So for prediction, I use two figures from Hemi's study, which is very nice. These are the predictions from ECMWF model and NSAM model. Basically, there are two major errors. One is the phase angle errors. Here, we are looking at the difference between the model forecast, phase angle error, and observation. Now, you probably don't need to know what this means, but just need to know that the negative values here means the propagation speed is too slow. And another thing is the amplitude. Overall, the model's amplitude, which is blue or red, are weaker than the observation for most phases. So that is prediction. So what are the factors affecting MJO and MISO simulations? There have been many studies on this, and studies have shown that the simulation of the MJO or intraseasonal oscillation can be affected by atmospheric physics and configurations, including cumulus convection, shallow convection, cloud radiation, and also there's some impact due to the resolution. One particular category of GCM simulations are all the simulations that use superparameterization, which shows improved simulation of the MJO. So that's a very good approach, but the disadvantage is that it's expensive. And the MJO is also affected by AS interaction, and studies have shown atmospheric respond to surface temperatures, and the ocean also respond to atmospheric forcing at the intraseasonal time scale. So when you compare the model simulations, the studies generally shows that the simulations are better in couple model than in atmosphere only model. So So in this study, in this talk, I will present results from our recent studies on the ASC interaction. It is generally accepted that the model biases, model errors in MJO simulation is more related to atmospheric physics, and the ocean ASC interaction is considered to play a secondary role. So now, why do we choose to analyze the ASC interaction? There are two reasons. One is the ASC interaction may be important, although not the primary factor. And second reason is that the ASC interaction is less difficult to understand. So the relationship among the fields are relatively easier to understand. So that's the second reason. So here we use a diagram from a recent summary review paper, which shows the relationship among the fields associated with MJO. So the rainfall is in gray the gray curve, and the SST is the cyan in cyan color, and solar radiation is in red, and latent heat flux is in green. So day zero means the time when precipitation is at its peak. So we have SST leading rainfall by 7 days or so, and SST are led by solar radiation, positive solar radiation, and also negative latent heat flux by 7 days or so. And these two components together help warming the ocean, which precondition ocean surface and support the propagation eastward of the convection. So that's basically the picture of ASC interaction. So what we are going to address, today we have 3 questions to address. The first one is how important is the accuracy of underlying SSTs in the simulation of the observed MJO and the MISO. And how does the accuracy of the simulated SST depend on the ocean model? And how important is the presence of the ASC coupling in the simulation, and how does the simulated ASC interaction depend on the surface fluxes that are affected by atmospheric convection? So basically that also gave us the outline. So we have 3 parts. The first part is about the simulating MJO and MISO with atmosphere-only model. That is to investigate the importance of SST accuracy. And then we'll use the ocean-only model to study the impact of the ocean vertical resolution. Then with the couple model, we talk about the ASC interaction. So the first part, that is atmosphere-only model simulation with specified SST. So we start with comparing 2 SS data sets. Both are observation analysis. This is a evolution for the Dynamo intensive observation period from October to January. We have 2 observational SST sets. One is NCDC SST, the other is TMI SST. And on the left is OIR anomalies, which indicate 3 nice MJO events. So the major thing we see that is SST, warm SST, lead anomalies lead enhanced convection, and another main thing I want to indicate is TMI SST is generally stronger than NCDC SST. So looking at the standard deviation, the TMI SST is about 0.1 or 2.2 degree stronger. So that is the Dynamo period, winter MJO active period. And we did a similar analysis for the MISO summer period, here is a composite for 7 MISO events. The upper left panel is the rainfall, composite rainfall for 7 events. Day 0 means when the rainfall has its maximum in the Indian Ocean and at latitude between 5 degrees to 10 degrees north. So that's the day 0. And we see a very nice northward propagation. And corresponding to that, we have TMI SST and NCDC SST. So both SST analysis showed the northward propagation too. And SST lead the precipitation by 7 days or so, similar to MJO. And again, the difference is that the TMI SST is stronger. This is standard deviation, stronger than NCDC SST by 0.1 degree or so. So we want to ask, is this SST uncertainty of 0.1 degree to 0.15 degree sufficient to cause significant differences in the simulation or prediction of the intraseasonal oscillation? So to test that, we carried out a bunch of experiments with and one atmospheric model, which is GFS at T126, horizontal resolution, and 64 layers. And we used 3 SST data sets to force the model. One is TMI, and the second one is NCDC, and the third one is just climatology. And we tested 3 convection schemes, simplified our Kawashima scheme, which is in operational CFS version 2, that is for climate prediction. And the SAS2, that's the revised version of SAS, which is now used in operational GFS, that is for medium range forecast. And in addition to this too, we also have another convection scheme which is called relaxed Kawashima scheme. This is not operationally used. And forecast runs are initialized from climate forecast system reanalysis. And the initial dates were for MJO experiments. We did this for Dynamo period from October to January, from October 2011 to January 2012. That covers 3 MJO events. And for the MISO, we have 7 events from 2001 to 2009. And the forecast length is 31 days. So for the winter MJO experiments, we first look at the RICE convection scheme using 3 convection schemes, compare that with observation. So this is OIR anomalies. We see that when the climate SST is used, the model was able to capture the observed variability to some extent. For example, the October event, MJO event, and the December event are captured to some extent, and the model totally meets the November event. And when NCDC analysis is used, it captured the November event now, and the October and the January event are still there, not much improvement. Now when TMI SST is used, the simulation becomes much improved, even compared to NCDC. And also that includes many details in the simulation. So TMI SST is the best set we used among the 3 sets. So so when we say we use the observed SST, it's still possible that different SST may lead to different results.
Just a question. So are these ensembles and how many members?
These are 4 members each day, and it is for the 3-month period.
So each day you have, these are all from day 12.
Right, this is all day 12 forecast. just reconnect them together. So it's data from each forecast. So now for the same SST, TMI, that is the best one, we also compare the impact of convection scheme. So when we use operational GFS scheme, the model captures the oscillations, but first it's weak, and the propagation is not well organized. And when we use size, it's improved compared to size 2, and the rise is actually even better. So it depends on both SST and convection. To quantify the comparison, we calculated the correlation scale for the Indian Ocean and Western Pacific. So this is a anomaly correlation for OIR. We have the results from size 2, size, and rise, 3 convections, and within each we have 3 curves. That is for climatologic SST, NCDC SST, and the TMI SST. And for all schemes, clearly TMI SST is the best, and NCDC is the second best, and the climatologic SST is the worst. And among the convection schemes, looks like the rise is relatively better than the other 2 schemes.
I have a question. So have you thought about whether it's this pattern difference or it's really the slight amplitude difference that you contribute? Because there seems to be a pretty big difference between.
It's both. Yeah, the rise has a relatively closer amplitude, and also better organization of eastward propagation. Like this one, you can keep saying these things. So it's
No, what I meant was the difference between TMI and NCDC SST, because the amplitude seems to be a small difference.
Right.
But are there a difference because of the pattern difference also?
Both, actually. Even the pattern is different.
Yeah.
But generally, it's I just call that the uncertainty. So it could be both. Yeah. And now for summer, I have 7 events, as I mentioned. And here we look at the prediction, average prediction for those 7 events. Here is the CMOF observation, which has northward propagation. And for model experiments, I have 9 experiments with the use of different SSTs and the different convection schemes. So when climatologic SST is used, the model does not really calculate that, capture the northward propagation. The model actually just produces stronger convection near the equator. Here, day 1 is enhanced convection at between 5 degrees north and 10 degrees north. And when NCDC SST is used, some kind of improvement for the northward propagation, although it's not well organized, but compared to climatologic SST, it's improved. Now, when we use TMI SST, it depends on the convection scheme. So for size 2, still not much there. The significant improvement is in this rise scheme. Now we see a much better propagation northward. So again, we also quantify this with correlation for the rainfall anomaly for the Indian Ocean. Basically, the comparison is similar. So we have TMI forecast the best among all 3 SST data sets, and also relatively rise scheme is better than the other 2 schemes. So in summary, we say that accurate SSTs are important for prediction of both MJO and MISO. This suggests that MJO and MISO simulations and predictions not only need coupled atmosphere ocean models, but also need the improved modeling of upper ocean with realistic SST. And such a dependence also rely on what model physics we use. For the three schemes we tested, right scheme turns out to be the best one. So next I'm going to talk about the SST variability with the ocean-only model. That is to investigate the importance of ocean vertical resolution. So why do we want to study the vertical resolution, impact of vertical resolution? There are a couple of reasons. First, atmospheric model simulations of the intraseasonal oscillation with TM-SST, which is defined as ocean skin temperature, is more realistic than in-situ SST, which is defined as bulk temperature, which is a few meters. So that's another difference between these two data sets. So their definition is different. And we also saw a few papers on the impact of vertical resolution on the simulation of observed diurnal and the intraseasonal SST variability, which shows that vertical resolution is important. Another reason is that when we look at the couple model, climate model simulations, most models, if not all models, use the 10-meter vertical resolution for the ocean. And all models produce stationary and too slowly propagating intraseasonal oscillation, as we just saw. So here I put together a list of the models that use the 10-meter resolution. All models that indicate the vertical resolution use the 10-meter. So I'm not sure if the models that did not indicate the resolution used 10 meter, but it's likely 10 meter is used for all climate models. And what we're going to do, we're going to test two resolutions. One is 10 meter, and there is 1 meter. For the 10 meter resolution, the resolution is 10 meters for each layer, which is from top to ZB, that is the bottom of each layer. That is 10 meter. And for the top layer, the temperature is calculated at 5 meter depth. So this is what is taken as SST in the model, in all models. And for 1 meter resolution, we have 1 meter resolution for the upper 10 meters, and the top layer is 1 meter, and the SST is calculated. The temperature is calculated as 0.5 meter depth. So that's a big difference. Looks like I need to do something like this. So the experiments we made, we use GFDR MOM5, and the forcing fields are hourly from CFSR and from NASA MERA. And we use just average of these two reanalysis. And the simulation period is Dynamo period from September 2011 to January 12. And the experiments we made, 2 rounds. One is 10 meter run, the other is 1 meter run. And the validation data is Dynamo Observations and the ROMA observations. Both are in situ observations. So first we look at the observed average diurnal cycle for the upper ocean. Here we have 8 in situ observations, or the calculations for the Dynamo period, and this is the average. 2 major features are that the surface temperature has a maximum each day in the afternoon, and related to this maximum, we see a very sharp vertical gradient within the upper 10 meters. So it is not possible for the 10 meter resolution to capture this feature. And what about the simulation? So we have, this is a comparison of the simulation with observation for one particular location, 1.5 south and 79 degree east. And I have observation here. And for the simulation, we have 1 meter versus 10 meter. That is for the entire period and for the entire period average. And first, the 10 meter model just missed this maximum amplitude temperature in the afternoon, and we almost cannot see the vertical gradient in the afternoon. And they observed the features of maximum temperature, and the gradient are very well represented in the 1 meter run. The left two columns are comparing the two periods. One is a warming period, and the other is cooling period. The warming period means when SST is warming up, and the cooling period means when temperature is cooling down. And we can see that the gradient and diurnal cycle, vertical gradient and diurnal cycle is much stronger during the warming period and then during the cooling period. So that warming period versus the cooling period basically means the intraseasonal episodes of a dry condition, a warm and wet condition. So this is the implication that we need this vertical resolution, high vertical resolution, to represent the intraseasonal variability. To see that more closely, we have the SST evolution at a particular point. This is comparison with observation of the simulation. 1 meter is blue, 10 meter is red, observation is black. So we see that intraseasonal variations of the SST, total SST. And this variation actually is more due to stronger or weaker diurnal cycle. So intraseasonal SST variation needs a good representation of a diurnal cycle. The lower panel is zoom in for a shorter period so we can see this more clearly. And here we see that the model sometimes can capture the observed temperature very, very nicely. And the 10 meter resolution diurnal cycle is way too weak. So looking at the two statistics, one is the SST diurnal range. We have 1 meter resolution. The diurnal range is about 0.5 or 0.2 to 0.5 degree, and the 10 meter is 0.2 degree. So the difference is 0.2 to 0.3 degrees. So that's the difference in diurnal cycle. And for intraseasonal oscillation, standard deviation, the 1 meter resolution run is about 2.2 or 2.3, and for 10 meter it's about 0.15. So the difference is 0.1 to 0.15 degree. So we see this number is really small. But remember, when we look at observation, the difference between NCDs and the TMI is also something like 1.1 degree. So we have shown that that is important in a simulation. So now we look at the evolution of the actual SST evolution for this dynamo period. The time goes from October to December. And here we see the 1 meter simulation of SST anomaly and the 10 meter simulation are very similar. And they have the same phase and for both positive and negative phases. And the thing is, the difference, we see that positive and negative differences. What's important is that the differences are in phase with the anomaly themselves. So that means the anomalies are enhanced in 1 meter simulation compared to 10 meter simulation for both negative and positive anomalies. So with that, this results suggest that to simulate this observed diurnal cycle and vertical sharp gradient within top 10 meters, we need a 1 meter vertical resolution. It is possible that if we use the higher resolution, the GCM simulation, which is now using time interpolation, may be improved. So that's my second part. So for the third part, I want to talk about the coupled GCM simulations. For here, I want to show some results we just got about the air-sea interaction. So what are the reasons for the model simulation error in terms of the air-sea interaction? Studies have shown that the biases in the mean state of the couple model may be responsible for the failure of MJO simulation. There are few of these studies. And it is also possible that the model failed to simulate the correct air-sea interaction because of weak SST variability, which is what we just talked about. And it is also possible that the surface fluxes associated with the surface fluxes are unrealistic, and those fluxes are related to atmospheric physical parameterization. So we have two questions to talk about here. One is how important is the presence of air-sea interaction when the mean state is the same, and mean state of SST is the same. There have been a few studies on the importance of the presence of air-sea interaction, but the way we took is different. You will see that. Another question is what is the role of convection parameterizations in maintaining the consistent SST variability through its impact on surface fluxes? So for this, we have carried out 5 experiments, and the models, we have 2 versions of the model. One is the standard CFS version 2, which is T126 for horizontal resolution, coupled to MOM4, which is a 1/4 degree by 1/2 degree for the ocean. And another one is lower resolution of CFS version 2, which is CFS V2L, which uses T62 for the atmosphere, and MOM4 at the resolution of 1/3 by 1 degree. It would be great if we use 1 meter vertical resolution for this. Unfortunately, we are not that far yet. So for this experiments, we still use 10 meter resolution. But since what we want to compare is for the convection, so that's pretty okay. So for convection scheme, we use 2 schemes. One is the size, simplified Arakawa-Schuber scheme, and the rise. So what we want to show is that this convection scheme result in different patterns in the surface fluxes that affect air-sea interaction, causing the inconsistent SST in a coupled simulation. So we have 5 simulations. The first one is standard CFS version 2 with size convection. So this is just the default CFS setting. And then we have CFS version 2 with different convection scheme. That is rise. So the only difference is convection scheme. And then we have CFS version 2 with rise, but at a lower resolution. So each each pair has only one change. So that helps us to identify the reason. Now the last two experiments are the same as the lower resolution with RAS scheme, but we nudge the SST to the climatology from the fully coupled run. So by nudging the SST to the climatology, we actually damp the SST variability. And the time scale we use is 1 day and 10 days. The one advantage of this is that first you can see the progressive change when you change the time scale, and also the mean state is almost the same with regardless of what time scale you use. So that is one advantage. So now we put together all experiments, and we look at the likely regression of different fields against Indian Ocean precipitation average for 10 degrees south to 10 degrees north and 70 east to 100 east. So that means we calculate regression against somewhere here of the rainfall. And you can calculate regression for different fields. So here we are looking at the precipitation, so the precipitation against itself. That is the shading. And regression for 850 millibars zonal wind, that is a contour. And we have observations in panel C, which is lower left. And we see that the model and the observation shows a very nice eastward propagation of rainfall and 850 millibar zonal wind very beautifully. That is observation. Now we look at the simulation from standard, not standard, from CFS version 2 with rice convection, which also looks very good compared to our observation, although it's somewhat weaker, which could be due to the SST amplitude is too weak in this model because we use 10 meter vertical resolution. And this is a standard resolution T126 and MOM4 at the quarter degree. And this one is the same as CFS version 2 rice, but with lower resolution. We see that the simulation is very similar. Both capture the observed feature nicely with a weaker amplitude. So by that, with that we can, and based on this experiment at least, we see that the resolution is not very critical for the simulation. Now we compare the right three panels, which is fully coupled, low resolution, with SST nudging runs, 1 day and 10 days. So you see that as you, sorry, this is 10 days and 1 day. So when you nudge the SST toward climatology, you damp the SST anomaly, and the simulated anomalies becomes weaker and weaker. So that means when you damp the SST anomaly, basically you suppress the convection, interaction. The model becomes incapable of simulating this variability. So that means air-sea interaction is very important. But we test this in a different way. Many models just compare fully coupled versus atmosphere only. So basically the conclusion is the same, but in different settings in the simulation. So now we compare the impact of convection. So we have RAS scheme, CFS version 2 compared to size standard simulation. So interestingly, now if we use standard CFS version 2 convection, the model sort of captures the propagation in the wind field. However, it's much weaker compared to RAS. And also the rainfall is also very weak in the maritime continent and the Western Pacific. So next I will focus more on these two simulations. So looking at the SST, That's the important field we want to look at. So here we have shading for precipitation, and SST is contour. The observed shows that rainfall propagation is led by SST by 7 days or so. So when you have convection in the Indian Ocean, you have warm SST in the Western Pacific or Eastern Maritime Continent. That's observation. CFS with the RISE scheme capture this very, very good, very, very well. So we see convection is here, then we have warm SST, and the model capture useful propagation. So CFS version 2 with size basically missed this SST anomaly. So that's the problem. So what caused that difference? The SST is variation is related to solar radiation and latent heat flux. So we plot this for 2 simulations and observation for solar and for latent heat flux. So what I want to indicate that for solar radiation, the observed has enhanced downward solar radiation before the SST, which is shading. The radiation is contour here. So the radiation enhanced downward radiation lead SST. So that helps the warming condition of the surface. And same thing in the RISE. And the size is also similar. The model captured that to some extent. The main difference is the latent heat flux. So in the observation, we see that positive latent heat flux that help the warming of the ocean in the observation and in the RISE simulation. However, the size, it's actually negative. So that is why SST is not good. If we look at more details of the time evolution, that becomes even more clear. So here we compare the average for the Eastern Maritime Continent and the far west Western Pacific, the average. That is a correlation with Indian Ocean precipitation. So what we expect is at day 1, before day 1, we want the heat flux to be positive to help the development of warm SST in the Western Pacific. So in observation, which is a blue, we do see this positive latent heat flux. And also in RISE, we also see that, which is very nice. Actually, RISE has a very good phase comparison with the observation. However, for size, we have very negative latent heat flux 10 days before the day 0, which is bad. So now, if we want to look even further, we decompose the latent heat flux into 2 terms, linearized. One is related to Wang anomaly, and the other is related to the anomaly of vertical humidity gradient. And we compare these 2 terms. The humidity vertical gradient term is very small. So the main the variation is dominated by the wind variation. So next I will show you a diagram showing the wind difference in this 2 rounds. This is probably very confusing, but the main message is that in the observation, we have the total wind field, total wind speed, that is positive. We have a minus sign here. Actually, it means weaker wind. That contributes to weakened latent heat flux before 10 days before the convection and peak convection in the Indian Ocean. And for this total wind field, we have contribution from both zonal component and meridional component, which is in blue and in green. So both components contribute to the total wind amplitude change. And this feature is well captured in RICE. So zonal component and the meridional component and the total are compared very, very nicely with the observation. And in size, first it produced two strong negative components for the zonal wind, and its meridional component is positive, but it's too weak. So that is my part 3. So in summary, we need ARC coupling for the simulation of the propagation across the maritime continent. And both zonal and meridional wind anomalies must be correctly simulated to produce realistic surface latent flux. The reason I want to indicate this is most of studies only talk about the zonal component. The meridional component is less focused. So coupling alone, having a couple model alone is not sufficient. We also need the convection scheme such that it has a correct surface heat fluxes for the correct ARC interaction. So that's what I have. All results are summarized in 3 papers. One is published, the other 2 are being reviewed. Thank you.
Okay, so yeah, let me first ask you a question. Yeah, in our discussion, so you were indicating that the CFS version 2 is probably not going to change in the next few years. So your results do show that the RAS scheme seems to be much better than the SAS, which is the standard scheme that is used to in the CFS. So are there any plans to sort of implement that, or?
There's an issue in operational center. When you look at when you investigate the different aspect, ISO, MJO, or Arctic oscillation, you always find certain approach or method scheme is better. But when you talk to people who is in charge of upgrade of operation model, they want a full assessment for all modes or anomalies, North American climate. So it's very difficult to push for a change, a particular change. So one alternative is, okay, since RAS is good, we need better ocean representation. So basically we can develop an experimental version so for experimental prediction. But whether it can be used for operational implement, it's a very different category issues. Yeah.
But RAS is already there, right?
Yeah.
RAS is already there. All we do is just
implement, yeah.
Exactly. But people may argue that, what about easterly wave? What about the cyclone? Other things. So since we don't evaluate that, they don't buy it. Unless you evaluate everything. But we cannot do that.
Yeah.
Yeah, I just wanted to ask about this ARC interaction. Does RAS have, or is there any gustiness feedback? By convective,
That I didn't check. But the gustiness, I think it's extrapolated to the surface. Then there's a what's that called? 5 meter or something minimum. So if it's less than minimum 5 meter, it's just 5 meter, something like that.
meters per second.
Yes. But I look at the anomaly and total field. It seems, I mean, that may be a factor too, but it seems the anomaly is still there, even both use the same gustiness.
5 meters per second is a pretty big number.
Yes. Yeah.
So it could artificially inflate.
Yeah, maybe we can make another experiment, turn it off, see what happens.
You showed that the latent heat flux is important.
Yes.
Can you go back to the equation?
This one?
The equation.
Oh, you mean this? This one.
So, so the other one is the mean state, right? The vertical gradient of moisture.
Yeah, this is just like a mean state.
So in RAS and SAS, have you compared the mean state? That can be from the wind, but also from the mean bias.
That's a very good question. I think we did compare, swap the mean state versus anomaly. I'm not 100% sure, but I think mostly it's still just due to the wind. Even we can calculate the same thing with the mean state from another run. The anomaly is still dominated by this.
Yeah, I'm wondering because there's a mean state MJO trade-off issue. So the model which has good MJO has very bad representation of the mean state. Have you compared the
Exactly. The mean state, I think there's one run is a little too warm, the other run is a little too cold. So that's the difference. Yeah. Anyway.
Yes. Just relevant to this, very nice talk first. Next slide for the wind difference in those two runs.
You mean this?
Yes, this one. Yeah, I'm thinking whether the downdraft transport moments of transport due to the different cumulus scheme will cause different downdraft transport. So that gives us different zonal wind associated with convection.
You know what? We have been thinking what caused this. That could be the reason.
Yeah, right. That's a specific one. A more general one is about the interaction between ocean, AGCM, the ocean model. Basically, we're using much high resolution ocean components
Yeah.
to provide SST and the surface fluxes. Then through some kind of coupler interpolation, we provide AGCM with much coarser product.
Mhm.
So there's an imbalance between those two fields. Well, in your experience, Rich is very nice to use first higher ocean model, high resolution model, ocean model. Well, would it be possible just to use high resolution in the upper ocean levels, just up to mixed layers, such as using 1 meter resolution up to the mixed layer, not necessarily for the whole model?
No, actually, in this model, in the configuration I just talked about, it's for the top 10 meters.
Top 10 meters.
Right, not for the whole
all right,
ocean.
okay.
Yeah, only top 10 meters.
How much more expensive is it?
Nothing, negligible.
So why not?
Yeah, why not? That's right. So I want to implement this, but
Well, it's not
I need to
another
talk
one.
to so many people.
Yeah.
Once again, right?
Yeah,
Then
that's
you
right.
probably have to run it for a few years and then
Yeah.
see whether it impacts other things.
Yes.
Very good.
Yeah.
Right. Also, the high resolution input from the ocean model could be configured in the convection scheme, such as we just use a high resolution input from the ocean model to drive the convection, such as under the ST concept.
Yes. Yeah. Yes.
Right.
This might be a question more for Murat, but I mean, how much more expensive is the super parameterization? How far are we?
About
Oh.
100 times.
What's that?
100 times.
100 times.
Power doubles. Well, I don't know.
But it
And
can
if you
use
think
about
about
100
the
times
growth
more
of-
processors.
I'm sorry?
It can use 100 times more processors. So in terms of wall clock time, it's about 10 times slower.
Yeah. So, and it ends up just got a new computer and other thing. I'm just wondering, how far are we from at least going to that?
It's already been done in the caller right now.
That's what I thought. So, I mean, I mentioned this to other speakers. This convective parameterization issue is really troubling, right, in terms of the sensitivity to that. And
Yes.
So as a useful experiment, as well as maybe operations eventually, is trying some other things where we have a fighting shot at getting the MJO,
Yeah.
strength and
Yeah.
propagation.
Murat I just talked to Murat. Cola is testing this, which is good. results will come out soon. Oh, let's wait and see. And NSEP like to hear more from outside than from inside. If I talk to NSEP director, hey, we want to implement this, he just ignore it. But if you talk to him, he would take it seriously. So just talk to him.
So, yeah, okay, I think let's continue this at lunch. So lunch will be at October again. Oh, no, 1:13. So again, reminding the students, there's 1:45 to 2:30 meeting with the summit with speaker Dr. Wang after lunch in 1:13. Okay, see you there. So we just break some.